Welcome AP Chemistry students. This is another installment of our virtual learning. Again, I encourage you, if you're watching this on YouTube, which you are, to subscribe to my channel. Hoping I will go viral, not coronaviral, but I hope that this will go viral in some way, shape, or form. Okay? So, what we're going to do today is we're going to review the Imf worksheet that was assigned to you. Just kind of go over it. I really believe that this is one of the areas that I think they'll focus on. This is one of the top important areas. So there will be, in my opinion, just some kind of free response questions dealing with this. Now, these first one is just super easy. Obviously, this is a solid, liquid, and a gas, okay? And so we can label that. Now, I don't like the way this question is worded because I disagree with it. The attractive forces do not change from a solid to a liquid to a gas. The kinetic energy, the energy of the molecules change to where it gives them enough energy to overcome the attractive forces. The attractive forces become less significant. So, but to answer this, in which of the physical states are the attraction particles atoms stronger? They're most significant, they're the strongest in solid, and they're going to be the least significant because they just have so much energy to overcome them in a gas. Okay? But the attractive forces do not change within molecules, and teachers all over the country ask the questions in this way, but I just disagree with it. But just kind of know that. Okay? So that was just so easy, we don't even have to spend hardly any time on it. All right, so now when we look here, if we look at, this is an ionic bond obviously, this is a covalent bond between the carbon and the hydrogen, okay? And then when we go to the next page, see if I can keep both of them on here. Get up underneath. I'm working on it here, hold on. Adapting. Okay, let's just make it a little bit smaller. All right, so if I'm looking at group A, I just have these, but group B, we're showing here the bonds between molecules, okay? And it also shows over here, this is kind of an important thing, look at the difference in the strengths of those bonds, okay? So, you have your sheet, hopefully you're looking at your sheet. I can't have all of this showing up here, but the next question asks for, it says, okay, intermolecular forces are non-covalent interactions between molecules. Which group consists only of intermolecular? Inter meaning between. So obviously group B are intermolecular forces, whereas this is an intramolecular force. Then obviously, which ones are stronger? Well, it's real obvious here. These are stronger. Okay? This is another big important concept that AP always wants to ask, you know, because they want to make sure when you ask the question, okay, so which are stronger, group A or group B? Obviously group A, okay? But then it says when you're boiling water, which bonds do you think are breaking? Covalent bonds, when we boil water, we've talked about this a bunch. When you boil water, what's in the steam? It's still water. So we're breaking intermolecular IMFs, where you're not breaking the hydrogen to oxygen intramolecular or the covalent bonds. So we just need to make sure we recognize this. London dispersion forces, notice they're the weakest. Okay? Then you have a hydrogen bond, which is the strongest, and then just your dipole-dipole. This is the negative end, this is the positive end attracting here. So I think that's pretty straightforward for you. All right. Now, looking here, and we're going to have to go on now to the next question dealing with these. Okay, so there's that graph. Okay, so again, whenever we see a chart with boiling points, higher boiling point always means stronger attractive forces. Now, all of these are kind of following a trend, okay? But, so when I say question 8, assign each molecule as whether it's polar or nonpolar. Well, how do we do that? Well, hydrocarbons we know are nonpolar. Chlorine, fluorine, oxygen, phone call. Now, do not say it is polar because it has phone call. AP is not going to know that. Okay, that's my deal. Okay, it's polar because they contain the highly electronegative elements of chlorine, fluorine, and water, and the shapes of the molecules are asymmetrical. Okay, that's how we know it's polar. But we just look; these are all just polar molecules because they contain highly electronegative elements such as chlorine, fluorine, and oxygen. Don't say it's polar because it has fluorine in it. Okay, that's not enough. Highly electronegative. That's the key. You got to say that. Highly electronegative elements of chlorine, fluorine, and oxygen. Get that into your head. Okay? Now, the more polar the molecule, the higher the boiling point is. Okay? The more polar the molecule, the stronger its IMFs. Okay? Because it's going to make a stronger, greater Coulombic attraction. The greater the charge, the greater the attraction. So those are all pretty straightforward. Now, which do you predict will have a higher boiling point, CO2 or CO? Okay? Well, CO2 is 44 grams per mole, non-polar. CO is only 28 grams per mole, but it has a little bit of polarity in it. So that one's kind of a tough question. You wouldn't be expected to answer that one. I'm going to say CO2 just because it's heavier and the polarity of CO is not going to be very much. But again, you're not going to have to compare, so don't worry about question 11 too much. I like these tables. We have to learn how to interpret the table. Again, when I'm looking here at my boiling points, I know that this highest boiling point has the strongest attractive force. Okay? This is the weakest attractive force, negative 188. So that boiling point tells me that. So you always answer these questions based upon whichever one has the highest boiling point. In years past, they've been asking where you have a small, something like CH3Cl, which is going to be polar, compared to something like C8H18, which is nonpolar. But if you were to compare the boiling points of these, this is going to have a higher boiling point than this one. Because it's so much bigger, the London forces here are greater than the London forces between the London and dipole-dipole attractions here. So if this said this was the boiling point, and you may not even be able to see what I'm writing over here. If the boiling point of this is, I'm not going to make up some numbers, it's 50, whereas this one is 80. Okay? So I can't tell if you can see that or not. Little adjustment. No, you can't see that. So what I'm saying over here is if we have those two molecules, okay, then you look at the boiling point, whichever one has the higher boiling point, even though the top one's polar, the bottom one has a higher boiling point, so its London forces are going to be greater than the combined dipole-dipole and hydrogen bonds. Okay? So that's very, very, very important. That is something that I would bet a nickel on that they're going to ask. Okay? So, all of these are halogens bonding to itself. They're all going to be nonpolar. Okay? Now, again, we know the strongest intermolecular forces is going to be I2. Okay? Since they're all nonpolar, the only type of attractive force is, scream it in your bedroom, scream it wherever you're watching this, nonpolar molecules, only type of IMF, London forces. Good. Second question, London forces, what do the strengths vary? Well, it's going to be the molar mass. It's going to be the bigger, it's not, let me take that back. It's not the molar mass, it's the size of the electron cloud. Okay, the size of the electron cloud. Bigger molecules are more polarizable, more squishable, and so as a result they have greater London forces, which are sometimes called induced dipole because they're forced to get out of whack. And so iodine has the strongest. They're all nonpolar. Is there a relationship between polarity and boiling point here? No. What is the relationship? The bigger the molecule, the more electrons in the electron cloud, the more polarizable it is, the stronger the LDFs are, and the higher the boiling point. Non-polar molecules, it's based upon the size of the electron cloud. Bigger molecules have more electron clouds. Here's the key word, they're more polarizable, and so they're going to have a higher boiling point. This to me is super, super important. So you go down to number 16, and it says, as the molar mass of a compound increases, the strength of its intermolecular forces increases. But the reality is it's not based upon the molar mass. It's based upon the size of the electron cloud. So we really need to say, and I would scratch through this on your paper, I would say as the size of the electron cloud of a compound increases, then the intermolecular force increase. Okay? Because if you just say it's got a bigger molar mass, you're not going to get your point, which is nitpicky, but AP is very nitpicky on that question. Okay, so moving on. Here we go. Another table of selected boiling points. Again, you can see as the molecule, the compounds are increasing in size, the strength of their boiling point is increasing. Okay? So, does the statement you completed in the previous question agree with the data presented here? Yes. Helium, neon, argon, krypton. If you note on your periodic table, that's the noble gases going down. The molar mass is increasing. The size of the electron cloud is increasing. Therefore, the boiling point is increasing. Here are your hydrocarbons. They're all non-polar, London forces only. Obviously, molecules are getting bigger. Electron clouds are getting bigger. Therefore, the boiling points are getting bigger. Now, according to graph 1 at the right, okay, let me move this up a little bit. This graph is right off AP test. Okay? Right off the AP test. So we're looking at this graph. Notice there's a general increase here. But there's an anomaly right here that water is super high. You would expect water, if it was going to be following the same track, to be down here. But what does water have that these other molecules don't? The answer to IMFs is almost always, wait for it, hydrogen bonds. All right. So which substance is there stronger intermolecular forces, SNH4 or CH4? Okay, SNH4 is up here. Well, this is the boiling point's higher than here, therefore it's got stronger attractive forces. Higher boiling point, stronger attractive force. Okay? Now, it's bigger, so the London forces, these are all nonpolar molecules, so the London forces are stronger because it's got a bigger electron cloud than this, but it also has a higher boiling point. So, in which substance are there stronger intermolecular forces, SNH4? Because it's got a higher boiling point, therefore the molecules are held more tightly. You can also say it's a bigger molecule with larger electron cloud, therefore its dispersion forces are greater, and as a result it's got stronger intermolecular forces, but it's all based upon the boiling point. It's based on, according to the graph, since it's giving you a boiling point, I would use that as my answer. Now, explain based on what you have learned so far why your choice should have stronger intermolecular forces. So this is higher boiling point, this is bigger molecule, bigger electron cloud right here. So that's going to be based on boiling point. This is based upon the size that SNH4 is a larger electron cloud, therefore it's more polarizable, stronger London forces. Okay? Now, going to question 19. The bottom line in graph 1 shows one trend, and the top line shows a very different trend. Which has stronger intermolecular forces, H2S or H2O? Well, obviously H2O has got a much higher boiling point. Okay, it's way up here. Okay, now explain why, mostly due to polarity or molar mass. Use 1 or 2 complete sentences. Explain why. Well, water, the answer again is hydrogen bonds. Water has hydrogen bonds, and so which are much stronger than the dipole and London forces of H2S. And H2S actually probably doesn't even hardly have any dipole. It has very little. Now, you're not going to need to know this, but sulfur's electronegativity is 2.58, hydrogen's is 2.20, so it's a difference of 0.38. Not much difference, but enough to where it would have a dipole moment, but very weak. Okay? But you really just have to say water has hydrogen bonds, whereas H2S does not, and therefore the attractive forces between the water molecules are much stronger than between H2S molecules, and as a result, it has a higher boiling point. Okay? That would be your explanation to number 19. All right, we're zooming. Okay, here's the same version of that graph, just a little bit more complicated. Okay, so which three compounds deviate from linear relationship? Well, it's the H2O, the HF, and the NH3. Now, you can't read it on this, but you have it on your sheet there. And again, the reason for all those, F, O, and N, is hydrogen bonds. Okay? This indicates the three listed in part have stronger intermolecular forces besides hydrogen. Which other elements are in these compounds? That's our phone, fluorine, oxygen, nitrogen. So that tells me they have hydrogen bonds. So compounds containing a hydrogen atom bonded to a fluorine, nitrogen, and oxygen form very strong intermolecular forces called hydrogen bonds. Are hydrogen bonds the same as covalent bonds? Absolutely not. A covalent bond is intramolecular, hydrogen bond is intermolecular. So if not, are hydrogen bonds stronger or weaker? Obviously they're weaker. We saw the chart at the top. They're significantly weaker. What was it? The value of 40 for a hydrogen bond versus 600 or 800 for an ionic and covalent bond. So it's significantly smaller, okay, weaker than a covalent bond. So that's important. It's the strongest of the IMFs, but compared to a covalent bond or an ionic bond, very, very weak, okay? I think I only assigned through 20, okay? So, but when it says here on 21, compare the boiling points of ammonia and SbH3 in graph 2, but which is more polar? Obviously nitrogen that's one of our big four. Nitrogen's going to be more polar. Which can form hydrogen bonds? Well, ammonia can form the hydrogen bonds, and based on polarity and hydrogen bond, what do you expect should have the stronger intermolecular forces? Well, obviously NH3. This one is only going to have London forces. Now, which is shown in graph 2 to have stronger intermolecular forces? NH3. Okay, it's got hydrogen bonds, the other one doesn't. Now the London forces of this one is going to be greater than the London forces here, but the hydrogen bonds here, and there's 3 places to form those hydrogen bonds, that's what kind of wins. Okay, so that's a quick review of those 20 questions. I want to just show you now just a few more questions off of actual AP test. Let's just kind of look at that just as a review as we're reviewing IMF. So if we look at this question right here, this is a multiple choice question. Given these compounds, now notice they give you the molar mass. When you have the molar mass given, that is an indirect way of saying they're about the same, therefore their London forces are going to be about the same. The size of the electron clouds are going to be about the same, okay? But we can see very different structures here. Here, total hydrocarbon. This one has an oxygen, this one has an OH. So automatically we know that this one has some hydrogen bonding in it. This one is totally nonpolar, only London forces. And this one has the oxygen, but it doesn't have the OH, so you're really just going to have dipole-dipole here. So based on the information table above, which compound has the highest boiling point and why? Well, we're going to pick propanoic acid because number one, it's got the greatest molar mass, so in a small sense, it's got the stronger London forces. But because it can form the hydrogen bonds, it's going to have a much higher boiling point. So the answer is going to be hydrogen bonds. Let me see. So propanoic acid because it can form intermolecular hydrogen bonds. Okay. Butanol. Notice here, butanol. Okay. It can form intermolecular hydrogen bonds. They're saying no, it doesn't have the OH. They're not giving credit for a hydrogen bond on that one. Okay. It's going to be this one because it can form the hydrogen bond. Okay, so we need to know that. All right, let's look at another one. Okay, got to zoom down to page down. All right, so here are some good ones here. Okay, 14 through 7, we don't need to see that. I'm coming. This is where I need someone sitting at my computer driving. And Emily Zhang, this is for you. Yes, I'm staying stocked. No virus, no nothing's going to keep me from having my Mountain Dew. All right, so I look here. So notice the boiling point, 351 versus 338. I automatically know this one's higher. They both have an OH, but this one has more, it's a bigger molecule. So what's going to be different between this one and this one? They both have an OH, they both have hydrogen bonds. The only thing that's different is going to be, this is going to be bigger electron cloud, so the London forces of this one are going to be a little bit greater. So equimolar samples of methanol and ethanol are placed in a separate, previously evacuated, rigid 2-liter vessel. Each vessel is attached to a pressure gauge, and the temperatures are kept at 300 K. In both vessels, liquid is observed to remain present at the bottom of the container. So in other words, it doesn't all evaporate. The change in pressure inside the vessel containing methanol is shown below. So in other words, it's evaporating, evaporating, evaporating. What does this mean once it gets horizontal? What does it mean? Well, it means, you guessed it, it's at equilibrium. So it reached equilibrium. So this is the equilibrium vapor pressure. 0.196 atmospheres at 300 K is the equilibrium vapor pressure of the CH3OH. Okay? Now notice that it just doesn't change once here. So we have, it's evaporating, condensing, evaporating, condensing. As long as we keep the temperature the same, the vapor pressure is going to stay the same. So now let's see what the questions ask. And I wish I could advance this, but I can't. I gotta move on here. Okay? So you have that graph in your brain. Okay, it went up to 0.196. So which of the following best describes the change that takes place immediately after the methanol is introduced into the previous evacuated container? This is what I'm talking about. So you put the liquid in. Okay, so we're going. So we put the liquid in, and if you remember the graph, okay, I'm going to put the graph here. The graph looked like this, and then it went level. So they're talking about right here. Okay, this is your pressure, and this is just time. Okay, so it's evaporating, right? We said that immediately it begins to evaporate until it gets to equilibrium vapor pressure. So is evaporation a chemical or a physical change? Well, it's a physical change, so I can eliminate those two. And when something evaporates, like water boiling, liquids evaporating, are you breaking, is it still methanol as a gas, or are you breaking up into carbon, hydrogen, oxygen, all those? Well, no, it's still methanol. So it's a physical change because you're breaking intermolecular forces. Okay, again, AP is going to ask a question. They love asking questions about that. Okay, now the value of Kp for the evaporation of methanol at 300 is closest to, we don't really have to, we won't talk about that right now. We'll come back when we deal with the equilibrium and look at that. But now I raise the temperature from 300 to 400. Well, what's going to happen to the rate of evaporation? Well, obviously it's going to go up if you increase the temperature. So the experiment and it increases the pressure from 0.196 to 0.3. The experiment is repeated under identical conditions, but this time using half the mass of the CH3OH that was used originally. What will be the pressure in the vessel at 400 K? Well, we're making the assumption that they said there's always some liquid left in the bottom. So if there's always some liquid left, the amount that's going to evaporate is always going to be the same. The vapor pressure stays the same if it's the same temperature. So this is a little bit of a trick question because it's going to be, we're having to assume that it doesn't all evaporate. There's always some liquid in the bottom, and it said that up at the top. So it's going to end up being 0.3 atmospheres still. So that's kind of the trick question. The whole point of this question is vapor pressure is dependent upon temperature. Same temperature, the vapor pressure is always going to be the same. Doesn't matter what size the container is. It's going to evaporate or condense to get to that exact vapor pressure, as long as there's some liquid left in the bottom. Now, compared to the equilibrium vapor pressure of methanol, the equilibrium vapor pressure of the ethanol. So what did we say? Remember we said ethanol was bigger. So that means its attractive forces are stronger. So what is that going to mean about its vapor pressure and its boiling point? Those three relationships between size, the strength of attractive forces, vapor pressure, boiling point, you must know those. As the strength of the IMF increases, so this has bigger London forces, so it's stronger IMFs in C2H5OH. Therefore, it's going to have a lower vapor pressure and a higher boiling point. So on our graph, the ethanol is going to look like that. It's going to have a lower vapor pressure. All right, so those are just some good questions. There's a couple more and then we'll call it a day. Let's go, 25 and 26. Oh, you like the graph? You always got a graph on there. I tell you, it's on there every year. I had to do this one just to show you this graph. This is, by the way, a different form of last year's test. Now, which of the following most likely described? So here I have positive and negative evenly in a crystal lattice structure. So what type of compound, ionic, metallic, covalent network, covalent molecular, do you think we're talking about? Well, obviously, hopefully you're knowing this is ionic. Ionic compounds have high melting points, they're brittle, they're electrolytes in water. So it's a brittle, water-soluble electrolyte that is a poor thermal electrical conductor as a solid, but an electrolyte means it conducts in the solution. Okay, properties of an ionic compound. It is soft and is a poor thermal and electrical conductor. That would probably be a covalent substance. It has a low melting point, it's a poor thermal electrical conductor as a solid. That again is a covalent. It's malleable and an excellent. Heat, thermal means heat. And electrical conductor is a solid. That's going to be a metallic bond on this one. This is your ionic bond here. Okay? Now, which of the following explains why CCl4 is a liquid where CI4 is a solid? Okay, so carbon, they're both going to be tetrahedral, they're both going to be symmetrical, so they're both going to be non-polar. That's whenever you're dealing with this, what are the attractive forces? Non-polar, non-polar. We just said 1,000 times. The bigger the molecule, the bigger the electron cloud, the stronger the London forces. So CI4 is going to have stronger London forces than CCl4 because it's got a bigger electron cloud, it's more polarizable. Now let me move that question up. I should have done the other one. Look at the responses on 26. Let me move it up one more. Which of the following helps explain why? Well, dipole moment, this refers to polar molecules. Both of these are symmetrical, so they're going to be nonpolar, so they don't have a dipole moment. Okay? The London dispersion forces are stronger in CCl4 than CI5? No. CI4 is going to be stronger than CCl4, which is going to be this one, D, the London dispersion forces. So you need to be able to identify the type of substance, type of attractive forces. Those are the things I think they're going to ask about. They're also going to ask a lab-based question, but they're going to put some of that in there, I think. Now, this graph, I doubt on the abbreviated version, this graph is going to be on there, but let me go up one notch. All right, so the Maxwell-Boltzmann distribution of molecular speeds. Okay, so we're talking about speed. Okay, so you got A and you got B. Which gas has the greater molar mass? Well, if you have a big mass, you ain't going fast. So B is going faster than A. The hump is farther to the right. Okay, B is a faster. Okay, if this was the same gas, B is the higher temperature, but two different gases at the same, B is the faster, which means it is the lighter. So A has the greater molar mass. Now, if another question asks, which of the following has the greater average kinetic energy? Well, that's going to be the trick question. They're going to be the same. Same temperature, same kinetic energy. But the bigger one's going to be going slower. Okay? So just know that about gases in your kinetic molecular theory and this Maxwell-Boltzmann temperature distribution curve. Okay? Now, almost done. let's go down to a free response question and call it a day. All right, the tables below show some data. Again, CH3Cl, CH3Br, very similar. This is more highly electronegative than this one, but this is a bigger molecule. Notice the boiling point of CH3Br is greater than the boiling point of CH3Cl. So I automatically know this one has the stronger attractive forces, stronger IMFs. Okay? Look at this first. Always look at the data. Higher boiling point, stronger attractive forces. We have competing things going on here. This is more electronegative than this. So that means the dipole-dipole, notice your dipole moment. That's a measure of your polarity. This one's more polar than this one because chlorine's more electronegative than bromine. But bromine has a much bigger electron cloud than chlorine, so the London forces are greater here. So because it has the higher boiling point and a higher heat of vaporization, in other words, it takes more energy to break the molecules apart, we know that this has stronger IMFs. Look at the data. That's why this question is so important. Look at the data. These are the type of questions I think they're going to ask because you can't look that up anywhere. So that identify all the types of intermolecular forces that exist. Well, they always have LDFs, always have London forces. They both are going to have dipole-dipole because they have dipole moments. Okay? Neither one has the ability to form hydrogen bonds. Plus, there's no hydrogen attached directly to anything anyway. Okay? So in terms of intermolecular forces, explain why the boiling point of this one is greater than this one. Since they both have very nearly the same dipole-dipole, but this is more polar, it's got to be because this has a bigger electron cloud, it's got stronger London forces. Okay? So when you're comparing, one is greater than the other, you have to look at the size of the molecule. A larger non-polar molecule or less polar molecule, because of the strength of the London forces is greater, it makes it have the higher boiling point. So please, look at the data. Higher boiling points, always stronger attractive force, bigger molecule, bigger electron cloud, greater London forces, makes it more polarizable, stronger IMFs. Okay? So, that's a great question right there. All right. That concludes this review of IMFs. Feel free to email me if you have any questions about any of this. I'll be glad to try to get with you and review as much as possible. And hopefully you guys are doing your work. All right? Well, we only got about 4 weeks left. You can do it. And I really, really miss seeing you guys in class. Okay? Have a great one. And remember to subscribe to my channel.